fact that it worked twice doesn't mean that it's going to work 3 times. Okay, welcome everybody. This is our third panel of the day, Next Generation Electrochemistry 2021 edition. Reminder of what we're doing here. This is another panel on research topics. Like I said, not all of them are going to be on specific topics. That we're going to have discussions on other things that are more related to soft skills. But in this panel, we're going to run the same way as the other two. Each of our panelists is going to give an opening statement, 5 to 10 minutes. The idea here is laying out a host of questions that are related to the topic at hand. And especially, we're looking for ideas on where electrochemistry is going. And then we'll have discussion, and we'll do the same thing. The panelists will discuss with each other. I'll moderate to make sure that we're touching on different topics. But then we have a set of participants in the Zoom call, and they're going to be free to ask questions. We're also live streaming on YouTube. If you're watching this and you're on YouTube, you can put questions in the chat, and we're monitoring that as well. We're going to run for 90 minutes, as we've done in the other two panels, and it worked well. Everybody's time is precious, so we'll stop at 4:30 Central. So for those of you that are our panelists, my request to you is that you spend as much time as possible discussing things that are at the frontiers of knowledge. Tell those in the call and those that may be watching us on YouTube, what is it that we don't know and we would like to know. It's okay to be controversial. It's okay if you don't agree with each other. That is an opportunity for discussion, and it's also an opportunity to show that that answers are not always clear-cut for the next generation of scientists who are in the room. It's also an opportunity to make sure that you convey a message of thinking critically and think about fundamental principles. We had a robust discussion on fundamental principles versus record performance in the previous panel. And the panel was adamant that fundamental principles are the most important aspect. So let's continue with that. For the attendees, you know the drill by now. Get involved in the discussion. You've been very animated in the two panels, so I'm expecting you to be as animated here. Don't think about whether the question is smart or not smart. Just ask it. Mute your mics while there's other discussion going on or panelist presentations. If you hear the sound of the panel twice, that's because you have a browser with YouTube open and it's automatically streaming. That happened to me in the previous panel, and so watch for that. When you're ready to ask a question, post in the chat of Zoom, and then I'll give you the floor and you can ask live. If you cannot speak because your mic is not working, let me know when you post on the Zoom chat. Be bold in your questions and think broadly. That's my charge to you. And that's it. We're going to get started. And as with the other panels, we agreed upon a set order before we started. And the first one to go with the opening statement is going to be Don Siegel from the University of Michigan. Don, the floor is yours.
Okay, hello everyone. So I guess there is a penalty for being prompt. That's okay. So let me share my screen. Okay, so hopefully, can somebody give me a thumbs up so I can, okay, thank you, Nitash, great. Let me put this in full screen. Okay, so yes, so I'm Don Siegel. I'm a professor of mechanical engineering from the University of Michigan. I also have appointments in material science and engineering and applied physics. And I'm a computational material scientist, so I thought I'd use some of my 5 minutes to mention briefly computation, some of the values, some of the value it brings, and some of the drawbacks that we also have to deal with. So this slide gives some of the big picture about why computation or how it can be helpful. And if you look at the left side of the slide, I'd say this is with the microscope. Characterizing and understanding is one of the maybe historical ways we've used computation to try and understand materials, to understand chemical reactions, Basically, we have some information. We know what it is we want to study. We probably have some experimental data that motivates our model or our simulation. And basically want to address a question, answer a question that would be difficult to resolve experimentally. So think of computation as basically another tool for gathering information where that information couldn't be gathered, say, using experimental techniques. Now, on the right, you see another motivating factor. This is a bit newer, using computation as a discovery tool or as a prediction platform. So here the concept is that in some cases, we can predict materials properties faster than we could using conventional experiments. So this is helpful. Sometimes we find things that look really good, which can go to our experimental colleagues and they can try to make and evaluate those materials. But also the inverse is also helpful. Sometimes we can screen many compounds and rule out maybe 80, 90, 95% of them that don't make any sense, that thermodynamically are dead ends or that don't have the properties that we think would be useful. So cutting down on the number of possibilities that our experimental colleagues need to explore is certainly helpful to them. So anyhow, both of these philosophies are still in use today. And well, maybe I'll show you an example of one or two of them later. So this is a panel on solvation, and I thought I'd show an example of where solvation is really important. Has been important, say, for the past 5 years and might be important for many years to come. So in this case, we're thinking of in the context of solid state batteries or solid electrolytes. So the solvating medium here is a solid, and we have in principle a cation, something like lithium or magnesium, that would move through the crystal structure of those materials. And the solvating ions more or less stay in place. And maybe some of the other panelists will expand on this idea in a moment. But speaking from an applications perspective, solid state batteries are really important because if we can get them to work, their advantages would be phenomenal. One advantage is safety. So if you look on the top left, today's lithium ion batteries that use liquid electrolytes, those liquid electrolytes are typically flammable and volatile. So I'm sure many of you have seen photographs or movies of electric cars on fire. A good chunk of that combustible component is the liquid electrolyte. So if we were to replace that with a solid, we generally eliminate that part of the safety issue. But beyond that, there's advantages in terms of energy density. And so this is shown on the right. So at the top, you have an example, and the areas shown here of these two cells are in proportion or drawn to scale. So on the top, you have an example of a conventional lithium ion battery with a porous cathode on the right. On the left, there's a porous anode, and you have a separator in the middle. And in principle, all bits of both the electrodes and the separator should be permeated by the liquid electrolyte. So in this case, if you try to estimate how much energy by volume and mass, you can see, I'm sorry, the number is very small, but about 150 watt hours per kilogram. That's the specific energy, and 250 watt hours per liter. That's the energy density. Now, if you could replace this liquid electrolyte with a solid electrolyte, and in that case, also replace the intercalated graphite, commonly used as the negative electrode with lithium metal, you see that the area or the volume shrink quite a bit. And in fact, that change in pack size going from 250 to 750 watt hours per liter, that's a factor of 3 improvement in energy density. So that would be phenomenal, probably worth another Nobel Prize for the person who's able to make that work. And then specific energy, the energy per unit mass goes up about 2/3. So this is the benefit. This is why solvation in solid state really matters as far as applications are concerned. And the good news is that we have an increasingly large number of pretty good solid electrolytes, ones where the conductivity is high enough for these to be interesting from a practical standpoint. However, as we found, despite this success in identifying new materials, there's still many issues to be worked out. And so this is basically an electrochemistry issue at interfaces to try and understand how do we get these solid separators, these solid electrolytes to play nicely with the two electrodes. And in particular, a big problem right now in the community is solving the so-called dendrite problem, where when the cell is charged, lithium metal basically creeps across the solid separator. Surprising that it could even do that, and in principle create a short circuit. And at that point, the cell is dead. So there's a materials discovery aspect here, looking for new solid electrolytes that would have even higher ionic conductivity. But also, I think a lot of the action nowadays is at the interface and trying to understand how to keep electrodes and electrolytes in contact, not reacting in deleterious ways, preventing dendrite penetration. And so let me wrap up and just show you some of the things that we're working on in my group. So this is just a brief introduction to my area of research. Again, we're a computational material science group. We do quite a bit of work on energy storage, mostly focusing on batteries or electrical, but we've done some work for many years in the chemical space, also in thermal energy storage. And one other thing to point out, I think it's important to recognize there are many different flavors of computation. In my case, we're focused more at the atomic scale. And even with that limitation, there's still quite a bit of diversity available in the techniques. At the top here, you can see density functional theory and quasi-particle methods. These are very accurate but expensive techniques. And as you go down, things generally get more approximate. With the quantum mechanical techniques, we, of course, don't make any assumptions about what the electrons are doing or try to minimize those assumptions. Other techniques such as Monte Carlo or molecular dynamics, we might prescribe the nature of the interaction between atoms. So that's a bit of a constraint or a limitation, but it allows the calculations to be much more efficient. We can examine bigger systems and look at phenomena that we can't when the system size is very small. And then finally, there's also the possibility of coupling techniques. So taking information we could pass at the atomic or electronic scale and passing it up to continuum or mesoscale models. Sometimes this is referred to as multi-scale modeling. So let me stop there, and with that introduction to my group, pass it off to the second panelist.
Right, thank you, Don. Our second panelist giving his opening statement is Nitash Balsara, who's from University of California, Berkeley, and Lawrence Berkeley National Lab. Go ahead, Nitash.
Thank you, Jordi. I have titled this presentation Liquid or Solid Solvation. It's interesting to be juxtaposed between a solid solvation expert, that is Don, and a liquid solvation expert, that's Kristin. And I thank the wisdom of the organizers for arranging us in this manner. The lithium ion battery that all of you carry in your pockets contains, as Don said, a liquid electrolyte. Not many of us realize that, I think many of you realize that the cell phone is basically a battery with almost nothing else. The electronics occupy a very small part of it. The display actually is somewhat significant, and maybe 20% of it. But in that rest of the 80%, 1/3 of it is a liquid. We don't realize that we carry that much of a liquid, but we do. And carrying a small amount of a flammable liquid is one problem when you have a Tesla and you have a battery that's 100 kilograms. Then carrying 33 kilograms of a liquid becomes a significant issue. So I want to point out that even though our batteries are big, even at the cell phone level, the lithium has to cross a barrier of about 10 microns, typically at this point. It used to be more like 20 a few years ago, and 50 10 years ago. But as manufacturing has become better and better, these solid particles are separated by a smaller and smaller distance. I don't show in this cartoon a a plastic bumper that is placed between the two electrodes. It's like a garbage can with a garbage bag with a hole in it, with a bunch of holes in it, to just fill the space with a liquid and allow these two electrodes to be safely separated from each other. Let me put a pointer here. There are, in addition to liquids, two other possibilities, polymers and crystals, and even glasses, but inorganic solids that are like flower pots or china, plastics like garbage bags, and liquids, of course, you all know. What the pioneers in this field do typically, and I'm certainly not one of them, is that you have to think at the atomic level, because in the end you make molecules of some kind. And the crucial question is, when the lithium ion is dissociated, which it must if it has to conduct, what does the liquid or material around it do? And so, in fact, many of the properties can be intuited by looking at what the surrounding atoms do in case of various liquids. Typically, the liquids will have oxygen. The starter battery in your car is a lead acid battery that is an acid solution, hence the term. And there the oxygen is contained in the water. It's always these oxygen atoms in the electrolyte that in the end interact with the lithium, solvate it, and take it, and are responsible for either allowing transport or blocking it. You can take a polymer with oxygen in it, these red guys, and again, if you look at the solvation shells, it's not that different, except now these red guys are tied to some other guys that are not oxygen, in this case, metal groups, CH2 groups. And then you have, an electrolyte that would, in the end, be, would look like a garbage bag between the two electrodes. And you can go all the way to a crystal, where again you have some sort of a solvation structure, and a crystal, is quite remarkable because normally when you think of a crystal, the elements of the unit cell vibrate in place. And in this case, all the little atoms and ions in this structure vibrate, except for the lithium ion that translates. So it's you might even not call it a crystal because one of them is translating. I don't know the formal definition, and Jordi can help us with that. So as I said, electrochemistry, invented in the mid-1800s up to right now, is dominated by liquids, these guys. But I think QuantumScape, which went public late last year in December, is the first example of a commercial entity solely devoted to taking a solid electrolyte system to the market. And so you can invest in QuantumScape if you have sufficient belief in solid electrolytes and what kind of batteries might be enabled by this these kinds of discoveries. I personally work on polymer electrolytes, so the garbage bag variety. And my motivation, and I have nothing to do with QuantumScape, and I have to get rid of this spam call, sorry. My motivation was based on solid state technology with regard to electronics. You see, when prior to 1947, all electronics was run on devices that looked like this, where you had a heated filament and electrons would go from the heated filament to the cold filament. And there were many complicated things in there, but basically that was a rectifier allowing electrons only to go in one way and that allowed for logic circuits to be built. And in 1960s, General Electric, that was one of the leading manufacturers of these devices, could boast and say they had like 20 pins instead of 8 or what you see here. It turns out that all of them were wasting their time. General Electric wasted decades perfecting the vacuum tube because they didn't pay attention to this solid rectification idea that came out of Bell Labs in 1947. And now all of the logic circuits that we use look like this. The only reason, one of the few reasons you would know that this is actually an object of commerce still made. It's made for guitar amps. I don't know if there are other applications, but my wife indulged in a guitar amp for me with a vacuum tube. I'm really afraid of when that blows up, or they all have a finite life. You see the lithium ion battery in the simplest manifestation looks exactly like this vacuum tube. It's cylindrical. When you contain a gas or a liquid, they're all round. A round shape is usually the best, and not quite in your cell phone, but in your laptops. They started with batteries like this. And in fact, the first generation of Teslas also ran on 8,000 of these laptop batteries. And in my lab, we worry about trying to make devices that are solid. They look like little flat plates. We have nothing to do with QuantumScape, but the question is, what kind of electrolyte would dominate the energy market in 2050 is an interesting open question, and the answer to which we don't know. That's where I want to leave you with.
All right. Thank you, Nitash. And our last opening statement, and definitely not the least, is Kristin Persson, who is also from UC Berkeley and LBNL.
Thanks, Jordi. Okay, so I am going to talk about recent advances in understanding of solvation and what I think we can go in terms of understanding and using our understanding to design novel electrolytes based on their solvation and their associated reactivity. So if you look at the first picture there, and I don't know if I can do the fancy thing that does this work? Can you see the spotlight?
Yeah.
Okay, great. So the pictures here are from papers. Papers are a few years old now, but I think this is fairly the prevalent view in the literature when you think about a lithium-ion electrolyte. The electrolytes that Nitash was talking about that you have in your cell phone, the sort of 1 molar lithium PF6 in some carbonate solution. And as you can see, it's a fairly it's a cartoon, right? You have the lithium, that's the red or the green little dot, and it's surrounded by solvent molecules. And there isn't really a presence of anything else except this one species or 2 species, the free solvents and the lithium bonded to its solvation sheet. Those are the 2 things that they consider mostly in these electrolytes. And that's where that's the picture I had in my mind when we started working on lithium-ion electrolytes and beyond, magnesium, calcium, aluminum, all those different kinds of electrolytes we might want to investigate if we want to go beyond lithium-ion. So I think this traditional picture needs change, and we have been looking into various variations, also appreciation for how simplistic this picture is. Even in normal lithium-ion electrolytes, there is the anion that floats around somewhere, and it's not as tightly bound to the solvent as the lithium is, but it's there, and it actually carries most of the current in lithium-ion electrolytes, which causes all kinds of transport issues that Nitash is much better expert on than I am. There's also what we call minority species. This is by far, the lithium surrounded by its solvation sheet is a majority species in terms of the lithium solvation. But there are minority species, even in these commercial electrolytes that we call, for example, aggregates or contact ion pairs. We tend to ignore them in the commercial versions because they're something like less than 5%, 10% of the species. However, what has maybe not been as recognized is that they can set limits on the reactivity of your electrolyte. Imagine, for example, that you have a contact ion pair. You have a PF6 that hangs out very closely with a lithium plus, and even though that's a minority species, the reduction potential and the oxidation potential of that PF6 is going to change because it hangs out with a very, very electropositive ion. And even though that's a minority species, if that's the species that keeps reacting, the equilibrium in the solution will feed that species and actually will set the limit of the electrolyte. And I think these are some of the insights that even though we think of them, it's just a small part of the electrolyte, who cares? And it may not matter for transport in some cases, they actually can be really, really important. And if we now go to the middle panel, this is a calcium electrolyte, calcium borohydride and THF. Here, these more cluster-like things, and you can see the neutral monomer with 1 calcium and 2 BH4 minus, and the neutral dimer, which has all kinds of 2 calcium and 4 BH4 minus. They're actually the majority species in this electrolyte. So it's not the simple calcium surrounded by solvent molecules. It's all kinds of clusters between the anions and the cations. And what we're starting to appreciate is that by tuning how many of each of these species and promoting, in this case, that little active species you see there that has a plus sign on it that actually carries some current, we can tune the activity and we can increase the conductivity of the electrolyte and keep it active with respect to plating and delivering the cation where it needs to go between the anode and the cathode. So we're increasingly entering this realm of there are more species out there, and for non-lithium electrolytes, they may actually be the most important ones. We can now go all the way to what we call super concentrated electrolytes, and we've looked at those for lithium too, because occasionally they have really important properties, like they can be less flammable, they tend to be more expensive because the salt is expensive, and they can actually, in some cases, promote transport, even though we would think that adding more salt to solution should slow down everything. But at some point, you change the transport mechanism. So you actually start hopping, for lack of a better word, of the ions in a network of connected anions and cations. So this is an exciting time to think about Solvation as a design vehicle. There have been some real advances in terms of not just understanding existing current systems and tuning them with respect to different solvents and salts, but also actually inventing new salts with this idea in mind. So we have, for example, for magnesium electrolytes, come up with what we call weakly coordinating anions that don't associate much. So you don't form these clusters much, but you have to go to very big and bulky anions to make that happen in a divalent electrolyte. So these weakly associating salts, they tend to plate better because they don't decompose, they don't expose the anion to the plating process, and we can change their chemical nature to achieve a high anodic stability versus the cathode. So a large electrochemical window, which means more energy density. So I want to highlight some of the works from Argonne, from Linda Nazar's group, and from Kang Zhu and Oleg Borodin on the super concentrated electrolytes, where they've been able to open up the electrochemical window of even a water-based electrolytes by basically protecting a particular species from being exposed to the reactivity at the different electrodes, or decomposing it very sparingly, and therefore change the way that the electrolyte operates and enabling higher energy density. So this brings me to my second slide. And Jordi asked us to state the largest or the biggest challenge in electrochemistry that's related to solvation. So I'm going to go straight for the worst problem I know, and that's the SEI, the solid electrolyte interface, which we have been studying for as long as the lithium ion battery has been present in our lives, even before its commercialization in the 90s. The problem is really that all of the electrolytes, and that includes many of the solid electrolytes that Don and Nitash were talking about, are actually not thermodynamically stable against the electrodes that we're working with. So you are going to decompose some amount of that electrolyte, whether it's liquid or it's solid, on your anode or cathode, and whether your battery works or not is all dependent on whether that interface that decomposition layer is electronically insulating and ionically conducting. And today we have no rational design principles for doing that. We just try and measure and try and have some rationalization after the fact why things work. So we're a little bit okay on the forward understanding. Like if you add this to the electrolyte, it might change that on these species, but we are nowhere near the reverse design. So I'm gonna just imagine if we could do this. And this is where I'm gonna connect to Don Siegel's introduction here. This is where computations might have a chance of helping us. So we can today compute more reaction pathways that you could ever imagine measuring. And we can hold them, freeze them in time and look at them and see if they matter or not. So imagine now a huge database filled of possible reactants and possible pathways, and using mathematically rigorous ways of searching through that database to the point where we can actually start characterizing what happens when the liquid electrolyte or the solid hits that electrode, either during just static or during the operation of the battery. And you can see how the reactions happen as water falling down a hill, and it collects a little metastable pieces, and then it just keeps on flowing. So that's where I think we need to go. I think we need to apply our increasingly data-driven methodologies to attack this problem that's been plaguing us for decades. So with that, I'll turn it over to the panel, and I hope I was provocative enough, Jordi.
All right, yes, that's great, because I posted on the chat, you probably just gave hope to a lot of the attendees, because in the discussion on electrocatalysis, one thing that came up was just how many parameters can influence the way that you can conduct a reaction on an electrocatalyst. So then we started talking about, adding, the cation that you add to the electrolyte can change your reaction pathways, and it started becoming very daunting. And so the fear that I was starting to have is, they're going to see these and just want to give up, right? Because there's too many things to optimize, and you just gave them a path which is applied to a different reaction, how this might be done, right? Because in the end, the STI is also a many parameter pathway that you need to be able to understand. And so perhaps this is another angle. So I put that on the chat so that they see that problems connect to each other. So this was very, very insightful. Before we open to questions completely, you said a couple of things, the three of you in passing, that I want to get your thoughts on and see if you can expand a little more. One of them is something that you said, Kristin, about how the anion carries the most current in electrolytes, because I think that this is something that if the students were listening, their heads probably exploded, because typically when you're building an electrolyte, you typically are worried about what the cations are doing, and the anions are, are they even there? And now you said that it's actually the opposite. And so want to share thoughts, and this is open to the three of you, not to Kristin just because she said it. Want to elaborate a little more on what you mean by this idea of anion carrying current?
Sure, I can start, but I'm going to invite Nitash to go right after me, because I don't want to bundle any of the transport theory that he knows much better than me. So the way that I think about it, in the lithium-ion electrolytes, lithium coordinates between 4 to 6 solvent molecules. And that's pretty big. That entity is pretty big, whereas the PF6 anion doesn't really like to hang out with the solvents at all, so it's much less bound. So from a conductivity perspective, one species versus the other, the anion zips through the electrolyte, and the lithium ion keeps dragging all these solvents with it. So that's really the sort of the underlying reason for it. If we were able to free the lithium ion a bit more and slow down the anion, which have been tried in polyelectrolytes and such things, then we could potentially reach a system where the lithium ion would zip more and the anion would be tethered or bound to something else. It's a complicated problem, because if you think you've solved one aspect of the problem, it typically these are very correlated systems. Even if you tether an anion to a backbone of a polymer, that whole polymer moves as one species, even if it moves very slowly. It still carries a lot of weight in that system. So Nitash, do you want to take over at this point?
No, I think you said it right. If the students have any specific questions, we can answer them. Great job.
So,
I've learned from the best.
I would turn the screw a little further and say, why exactly is this a problem? In the end, the lithium ion still makes it, right? So is this something that we should be really?
It's not great because you should care about it because you build up concentration gradients in your electrolyte, and eventually you can actually slow down the whole charge-discharge process because you remove the anion so fast that you have all the negative ions hanging out over there, and you have no interest of moving them where they should be going. So yes, it's a problem.
And again, is this an argument to use ceramic electrolytes then?
So single ion conductors, yes, where you don't have this problem is a real advantage.
Right.
Yeah, I think that that may be perhaps the most the biggest advantage that the kind of conductors Don was talking about has, which is that there is now, because it's a crystal, you don't have any concept of a concentration gradient, or even a glass for that matter, if only the one ion moves. I think it's a little bit complicated to figure out how the concentration gradients actually emerge from this disparity in mobility, but that's another question.
How does one go about? Is there an emerging strategy for designing? So aside from going to a ceramic all the way, what are the emerging strategies, or are there emerging questions that, if answered, could give us a strategy to favor that lithium transport or that cation transport over the transport that you don't want?
I would say that, I don't know how Kristin says it, but I would say a lot of people have tried and failed. In the end, the mixture that Kristin talked of, many people have come up with strategies to slow the anion down, but that always results in it also results in cation slowing down to the point where there is no net gain or even usually a loss in overall lithium transport. And so what you carry in your pockets, and it was invented in the 50s, is still the best electrolyte we know. All efforts to improve it have more or less, we have played at the margins, but not at the kernel. So our efforts to play at the, now Kristin may correct me, or even Don may correct me, but that's my understanding.
Yeah, no, I agree. And also, you can't just optimize for transport. The problem is that the electrolyte needs to do so many different things. And EC is one of the greatest SCI formers we know. So replacing EC with something that doesn't bind lithium as well is going to have consequences for your reactivity of the electrolyte, the electrochemical window, how well, and transport in the end is a composite problem, right? Even if you zip it up in the bulk of the electrolyte, it slows it down at the SCI level, you're screwed anyway. So it's not a one-dimensional optimization problem.
On that note, since you brought up EC, Lynn has a question on that. Do you want to, Lynn, are you able to unmute yourself and ask the question?
Sure. Thanks very much, Jordi. Dear all the panelists, thanks very much for sharing your valuable frontier thoughts on the solvation behavior. I do have a general question and wondering your opinion on this part. So as we know, we not only have the solvation behavior, but also the cation have desolvation behavior. And also I'm wondering your thoughts on the multivalence cation desolvation behavior in different electrolytes, and how will this affect the multivalent metal reversibility? Because based on my test, for the zinc, it seems like in different electrolytes, the difference is not that big, like what we saw in lithium ion batteries, for example, like the EC, PC on graphite part. So I'm really curious about your thoughts on this part. Thanks very much.
Do you want to should we just jump in, or?
Yeah. The questions are for you.
So I think that is a very good question, one that I don't think we've entirely answered yet. So the sort of flippant answer is, well, compared to lithium, we're dealing with a 2+ charge here. And of course, it's going to bind more strongly to the solvation sheet, whatever that is, if that's a solid or a liquid. But like you pointed out, zinc doesn't have nearly the same problems as magnesium and calcium. So just saying that we have a huge penalty for desolvation just because of the 2+ can't be true. So we are starting to, one of the things I think we can look more closely into is understanding what the interfacial reactions, or when the magnesium or the calcium or the zinc comes towards the interface and it's going to deliver its cation, it has to undergo some desolvation. And in many of these cases, you're dealing with these clusters, right? So it's not just the solvent, it's also the anion being dragged along. What is it that facilitates that? What is it on the interface of your electrode that helps to desolvate the magnesium, the calcium, and the zinc? And there's got to be a reason why zinc is easier and more close to lithium behavior than magnesium and calcium. So it's a great open question, in my opinion, and we haven't quite figured it out yet, whether it's as big as people claim. But Don and Nitash, you should tell me if I missed something.
So that's the second time that we say it's, about phenomena around solvation that we don't quite understand very well. One thing that clearly emerges from what you've all said is how poorly we understand solvation, even though we've treated it as a given for all this time. Do you think that the question of solvation at the interface, so the interfacial part has kind of appeared throughout. Is there something fundamentally different that you think you're gonna have to worry about at the interface that works different from the bulk? And if you understand the bulk, you might still not understand what it's doing at the interface?
Yes.
In what way, though? I mean, is it just about interface formation? Is it just because it's React and it breaks down and it's not the same thing? Or even if you were to
I think you should just leave it there.
Right. Well, you gotta give them clues so that they know where to go.
Right. Well, I think Kristin already touched on one of the issues, which is the sequential nature of charge transfer when you have a multivalent species, which, I mean, that's something that kicks in at the interface. But I mean, also going back to her opening remarks about an SEI or some sort of reactive layer there, that's different for every two electrodes and electrolytes that one brings into contact. And as was pointed out, we still really don't understand what's there. And if we don't know what's there, it's hard to say, what's the mechanism. There's a fair amount of guessing associated with that. And yeah, but let me just stop there and let the others jump in.
Yeah, I think that's the problem in a nutshell. We can imagine the actual process of stripping the solvent and stripping the anion from the active cation, but what does it bind to on the interface? And that's going to be maybe an evolving process if you have an interface that isn't entirely stable, so it keeps changing. And if that's the helping part, if you're binding your calcium to an oxygen on the surface, or you're binding it to something else, and that helps you to liberate it from its solvation sheet, then that is a crucial piece of it. And because we don't understand the interface evolution, this is a very difficult problem as well.
Nitash, what were you going to say?
What I was going to say is that Lynn, I think the student who spoke, has, a very, has great insight because the very fact that allows the ion to be dissociated, which is solvation, interferes ultimately with the delivery of the ion at the electrode, because there it has to get away from that solvation structure. So in fact, the better the solvation, the worse that step would be to de-intercalate. So you see, if anyone knows anything about that interface, it's probably Kristin. And if she says it's an open question, even without the SEI layer. The SEI is, of course, very complicated, but even in the absence of it, sometimes, especially in multivalent ions, we don't know what is the probability of it sticking inside the final host relative to this happy solvation that it has in the electrolyte. So it's beautiful to have all these devices that work nicely enough where we can make them work without actually understanding that process.
You gotta love that. We've accumulated a couple of questions, 3 now. Somebody just asked for a turn. So I'm gonna open the floor to some people. Aditya, go ahead and ask your question.
Thank you, Dr. Cabana. So I have maybe a broad question coming from, I work on the electrocatalysis side. So maybe it's the opposite end of the spectrum of electrochemistry here. But a lot of modifications to the SEI and were discussed here. My question is, do all of them involve any, are there still issues with the lithium dendrite formation with all of these? And keeping in mind, what would be like the trade-off between having a good dendrite suppression versus having the free lithium ion, freeing the lithium ion a bit more?
If I could take a stab at that, I think I'm not convinced that an SEI is present in every single, say, if we just look at solid state batteries. I think with liquids, maybe somebody could come up with a composition of an electrolyte that did not form an SEI, but it might not make for a very good or long-lived battery. In the case of some of these solid-solid interfaces between, say, the negative electrode and the solid electrolyte, I think there's a continuum of phenomena that exists there. There are materials that when you put them together react vigorously and can just continue to react until all of the reactants are consumed and you have no electrolyte and electrode left. There's the other extreme where there's no reaction whatsoever, or it's so small that one really doesn't care. There's no noticeable effect. And then there are cases in between where the reactions ultimately stop, they self-arrest, and depending on what is formed during that process, you may have a good situation or a bad situation. So yeah, that's the starting point. And depending where you are on that continuum, I think has a huge influence if your battery or other electrochemical device is going to cycle and be stable. And so, what forms, over what time period does it form, and what are its properties? I think that ultimately determines whether things like dendrites are a problem or not. And I think this is still something that we're trying to sort out, because there are tricks that could be played. So maybe temperature is a knob one could turn. Pressure is something one could apply to a cell that might retard the formation of dendrites. But it's still quite a bit of an active area of research, and I don't think we have a full understanding of what's going on. It's complicated, and I think it's pretty exciting because there's quite a bit to learn in this space.
Right there.
I have a comment, but I feel like Nitash should go first because he's done more work on
dendrites after you.
I have. Okay, I was really just going to say that I don't think it's always just a dendrite that grows from the nucleation on the lithium metal. I think there's an increasing body of evidence saying that as long as you have a defect in either your solid electrolyte, for example, or in your separator, you can start reducing lithium on that defect, and you're growing basically up from the separator or in your solid electrolyte. So there's not necessarily this sort of okay, there's a spike growing from the anode. It could be a nucleation event somewhere in your cell that's supposed to be electronically conducting. And that's really hard to protect yourself against. So Nitash, over to you.
Aditya, did you have in mind a particular electrolyte when you were thinking of dendrites?
Not Not exactly. I mean, I was thinking that I've been going through literature, and I couldn't find any connect between the is people are trying to modify their electrolyte again. Like this argument would come up again and again, like fleeing the lithium ion more. But I just wanted to see, like, you know, I understand a little bit that these two are both affecting the performance of a battery. Just wanted to know if they can be consolidated or they are completely treated differently.
I was hoping that would help me frame my answer, but the point is lithium dendrites can form on any surface. If you charge the battery that you hold, if you charge it fast enough, you'll get a lithium dendrite. And I don't think any an interfacial modification could slow it down, but in the end, not prevent it. Some years ago, when lithium batteries were being first deployed on an airplane, the 787, for about 7 or 8 months, that airplane was put in the garage because the lithium batteries were catching fire while the plane was in the air. And we don't know what happened because all of this happened behind closed doors, but John Goodenough went on the record saying that he believes that lithium dendrites were the reason for that failure. I haven't followed it, and I don't do forensic science, but so I think that malfunctioning batteries, lithium always tends to grow not in simple geometries, but in these fractal geometries. And how to prevent them, I have no idea. Once they form.
Are they, Don, just as a follow-up, I think it was you that mentioned that it may not always be a problem if you get a dendrite. Am I paraphrasing incorrectly?
I'm sorry, say that again, Jordi. You're breaking up a bit.
And it may not actually be a very, oh, sorry, my internet is starting to complain a little bit. I was trying to paraphrase that the problem of dendrites, it's almost sometimes a little overstated. Am I paraphrasing correctly, or is a dendrite always the death of everything? Is dendrite what we need to optimize against, or are we spending a lot of time working on something that we can manage instead of just preventing?
Well, I think it depends on the type of battery. If you give the lithium a home and have it intercalate, then probably you have to push the cell pretty hard, like make it very cold and go to very high, say, charging rates to form dendrites. It seems like the dendrite problem is not so much of an issue for conventional intercalation-based batteries, with the caveat that you put the battery in a bad environment or mistreat it, bad things will happen. My understanding is focused more on the solid state system, and that seems to be, it's a roadblock that we're hitting right out of the gate. Once we have started to see reports of solid electrolytes that have pretty high conductivity, the bulk properties of those solid electrolytes look good. And then the next step is, well, you put it up against an electrode and see how does it perform. And once you start to get to current densities that we think we need for a practical application, that's when dendrites were forming. We've learned a lot over the past 5 years that this comes back to the SEI, or just generally the cleanliness of that interface. Many of these materials are reactive with water and air, and if you don't handle them properly and then put them in a cell, you have this plaque at the surface, which ultimately that surface plaque gets positioned at the interface with the electrode, and that causes problems. So there are reports in the literature where people say they've solved the problem. I think you have to read those reports very carefully, because often, like, the temperature is high, or they've cycled very little lithium. They've plated and stripped very thin regions of lithium, which is, again, not the way you'd operate a practical battery. So I think there's a lot of caution that needs to be brought to bear in reading the literature. I think we're making progress, but I don't think it is a solved problem, and in my mind still remains a very important problem.
So we've touched on the topic of things that happen at the interface. And so we have a question in the queue from 1U that I think is going to be relevant to this discussion. 1U, would you mind unmuting yourself and asking directly?
Yeah, can you hear me?
Yes.
Yeah, I have probably a too general question. So it sounds like the solvation is going to be different in the bulk at the interface, and also when it intercalate or in the solid, across the whole device. So what are the current tools or techniques available to be able to probe the solvation in situ and operando, and what are the challenges or needed for improving those one? What are missing?
All right, who wants to take it on?
Great question. Not for a modeler, right? I can say
Nitash,
something. We've had
Right.
really good experience with NMR, working with people with colleagues that do NMR. So NMR is really good and it's a bulk technique, right? So it can get the speciation well characterized in the bulk. The problem is getting an interface that's large enough for that enough speciation at the interface. So I think that's a knob that can be more cleverly used, how to get enough of a signal at the interface. So very thin films of liquid on top of a large interface. That's all I'm going to say about that because I don't do experiments.
I was hoping Nitash would take that one, but I have something else to fill the blank space if needed.
Please go ahead.
Well, I was just going to say that I also view experiments as being perhaps there are experiments out there that are best suited to handle this problem, and I don't claim to know exactly which ones those are, and I'll hope that Nitash will fill those in. But some of the challenges with computation relate to basically the limitations and length and time scale. And sometimes there are components of the electrolyte that may be present in trace quantities that we don't know about in our simulations that could have a big effect. So yeah, we can make a model of maybe a salt in a solvent and run molecular dynamics and understand the solvation structure in that pristine environment. But when you go to an interface with an electrode, then things get more complicated simply because new phases might be present. The electrochemical environment is different close to an interface. So I would say the computation isn't, there are pieces of the puzzle one can unravel with computation, and the benefit is the atomic scale nature of those simulations. But they're just parts of it that really are best treated experimentally. And now I turn it over to Nitash.
Yeah, my feeling is that the interface is a very difficult subject to study experimentally. And I work a lot with lithium metal, and it's very common for people to declare that, this particular electrolyte that they just made is stable against lithium metal up to 8 volts or 6 volts or some number, crazy number like that, based on some data that they show where they show current versus voltage, and they're looking for some changes in the slope. The problem with that analysis is that if you take a flat lithium electrode and you put a flat electrolyte, liquid or solid, you don't have that much surface area. And in fact, many years ago, people sort of showed the qualitative difference between taking a slab and then taking a lot of particles where the area, just like your electrocatalyst, where you have lots of surface area, you just get a totally different answer. And when you get, so on the one hand, a flat slab has a very well-defined area. These particles don't have easily defined areas, but yet my feeling is that a lot of our understanding of voltage stability, if it comes from particles, I believe it. If it comes from slabs, I generally don't. And so while you're sifting through the literature, you might find this dichotomy in the literature. So it's a hard thing to do correctly, and I think the experimental and theoretical problems are the same. I mean, in the end, when two phases meet, most of everything, all the textbook stuff goes out the window. You can't average the conductivity. You can't, you have to draw normals, and you have to acknowledge kinetic parameters that are at least two values, and we have a hard time doing that. So I think it's a very good, it's a very rich and open area experimentally. Did I answer the?
Right. No, finish. Sorry, I jumped in too quickly. Go. Right. Finish.
No, I was just going to ask, is that a satisfactory answer? I don't know.
Yeah.
Is that satisfactory?
Yeah. Thank you for sharing this with me. I don't know much about so my previous project was working on solvation for supercapacitor. So in that time, but that was a very specific case. I used EQCM in the porous carbon, the quartz crystal microbalance. So we kind of indirectly measure the mass of the insertion ion, but this technique is very limiting. It's not easy to apply on any kind of electrochemical system. So yeah, and I think in the solid battery cases, it's I guess the most probably I've seen is NMR. I was just wondering if there are other ways to probe this this phenomenon. But thank you all for answering my question.
I will add to a couple of comments, and the second one is going to be redirecting the question formulated differently so that Kristin and Don cannot deflect to Nitash. The first one is, you've heard about, Kristin is getting mad at me. You've heard about, the importance of characterizing the catalytic systems. And if you look at that domain, you're going to see a lot of techniques that presumably could be used for this problem too. And so that's an area where you can start connecting fields. What you just said about using the electrochemical crystal microbalance is something that people are starting to play with. So it's not that far-fetched. The thing that I'm going to redirect is, and Nitash brought up the idea that once two materials become in contact, a lot of the models go out the window. So, are the models that we have now appropriate to handle that interfacial problem? Accounting for fields, accounting for, far from equilibrium phenomena. What's your take, Kristin and Don? If you wanted to calculate the reaction coordinate for an ion to be in the electrolyte and then be in the electrode, are we well suited for that?
I mean, not. I mean, yes and no. I mean, it's if I could just, my philosophy is that the real battery systems are complicated, and I don't think it's necessarily worthwhile to incorporate all of that complexity into an atomistic model. It may not even be practical or possible. Where I see the benefit of computation in this space is that you can come up with a simpler model that really probes the question you want to answer and strips away some of these complexities. So I've never been one to try and make an all-in-one model that incorporates everything that I think is happening, but really just probes what we think is important. So you can't take the human out of the model construction aspect. So, in this dendrite problem, for example, Kristin mentioned that nucleation of lithium metal can happen not just at the interface, but in other locations. So that might say to someone, well, really, we need to think about how electrons move through solid electrolytes that would be nominally impervious to electrons. So, that doesn't tackle the whole dendrite problem, but understanding that component of the problem, I think, is a bite-sized chunk that could be addressed sufficiently, and one could learn something from the output of, say, the simulation or the experiment that was probed to, attempts to probe that. So I would say, Jordi, your question isn't a fair one. I don't think it's one doesn't necessarily need a lot of complexity to gain understanding, and I think that's what we as scientists, that's the first thing we need to figure out, is what is the question we need to answer, and how complex does the model, or how detailed the experiment need to be to get to that piece of knowledge.
Do you want more comments on that? Yeah, I think I largely agree with Don. I mean, you can always throw more computing power at it. There are models who can deal with out of equilibrium potentials, rare events. It is a question of more computing time and more patience, but is it relevant to spend 5 years or trying to answer that question rather than addressing a simpler system where you can get an answer maybe a little bit more quickly, and that may be advancing the science more. So I think I would agree with that. And also, it's a real trap for modelers to try to address a system where if we don't know the structure and we don't know the chemistry, and that is notoriously true at the interface, then whatever simulation we do is liable for being completely wrong or irrelevant. Right. So we have to ask very careful questions when we set up those models.
And I will say that this has come up a couple of times in the other panels, the importance of articulating your hypothesis or the question that you're trying to answer carefully and not get carried away just because you have, a tool that can do something. So that's great. Anish, you want to ask your question?
Sure. Thank you very much. So I had two general questions. So my first question is regarding lithium dendrite formation in the solid state batteries. So when we say dendrite formation, we have high amount of nucleation on the surface, and when we say nucleation, the crystallization theories come into the picture. So the lithium dendrite formation, it means the surface energy of the lithium metal at the interface is very high. So is it not possible to control the surface energy at the lithium metal at the interface by coating it with some porous material? Let's say, off the top of my head, I can think of metal organic frameworks. So that's my first question. And the second question, which I have regarding finding the suitable candidates for the solvation. So as Dr. Persson pointed out, we are limited by the computational power. So can we not improve the search by using semi-classical methods or methods like group contribution and computer-aided molecular design like that?
Do you want me to start? I can start with it. Yeah, we definitely can. And my group, for example, does use semi-classical, potentials to figure out the solvation structure before we do any quantum mechanical calculations of the reactivity. And that is a great benefit of tying different length scales and different methods together instead of trying to address everything with ab initio. Because today we can't really run much longer than picoseconds with ab initio, but with classical molecular dynamics, even if it gets a little bit wrong, we know typically how wrong it gets there, so we can get an idea what is the landscape of speciation and then put that into a more accurate model for energetics. So I completely agree with that. There's no, I don't have a religious feeling about one methodology over the other. It's more about getting a relevant answer to the question. On the dendrite, I'm going to defer to Nitash and to Don, who have worked more on that.
I think that you might have even read the literature saying that a lot of people are generating these interfacial layers to see the effect on dendrite formation. Yeah, I think I want to stop at that point. I don't want to endorse or
not endorse the idea.
Jordi, you should push Nitash a bit further. He clearly has more to say.
Well,
Okay, Nitash,
I'll save
respond to that.
them of that uncomfortable interaction. I mean, the first part of the question was about the lithium surface energy. And I mean, I guess that could be important. It is important at some level, especially if the system is close to equilibrium. But I don't think this system, I don't think it's that important. I think this has to do with, it has to do with lithium arriving at that interface when you're charging the battery in an inhomogeneous fashion. I think the lithium gets channeled by defects in the solid electrolyte or by morphological differences or heterogeneity at the interface that gives one a really high current density at pinpoint spots at that interface, and that's where the dendrites grow. I mean, maybe there's a relationship to the surface energy that somehow contributes to the formation of those hotspots, but I think it's more than just the surface energy.
Norman, you had a couple of questions. You want to take the floor and go ahead and ask?
Yeah, thank you for taking the time. I'm a PhD candidate at Northwestern. I had a follow-up question related to the previous discussion, and then a second question that I guess I'll get to later. So I was thinking back to the sort of mosaic model, the SEI, that I think Paulette put out. And these like oligomers or like inorganic compounds that cover the electrode surface. The sort of computational studies that I've seen don't, at least the ones that I've read, don't incorporate like these other compounds on the electrode surface. They have like some oxide surface or some slab, and they have like solvent molecules that are solvating lithium ions, and they try to see what happens. And so my question was, what sort of insight do you have regarding ion solvation, knowing that there are like interfacial layers in the way, and our current like descriptions of solvents, or I guess like solvation, is that only true for like the first couple cycles? Like what happens when the SEI grows too thick?
All right, I'll start, but feel free to jump in. So yeah, I agree with you. I have not seen any model where people look at a true composite of the SEI and try to model lithium movement through that composite. And I think it's wise that we haven't attempted that yet, because we don't actually know what that composite looks like. And if we set it up in the wrong way, we're going to get the wrong answer, or we're going to get an irrelevant answer. I mean, it might be correct for that structure, but if that's not what's there, that's sort of may lead people down the rabbit hole. So what we first have to establish is what does it look like? We're sort of getting hints that it's lithium fluoride rich at the very, on graphite, on the very sort of beginning, and then you have LEDC and islands, and it oligomerizes that. So we have to figure out that part, so we can set up a realistic model before we even think about it, of moving ions through it. We can look at lithium ion movement through LEDC, right? But how relevant is that if there's a faster path somewhere else? Maybe it doesn't even move in the bulk of anything. Maybe it moves, like Don said, on the interfaces where there are defects. And starting to doing this by model systems, maybe that's a cleaner answer before we actually know what it looks like than trying to address a complexity that might just be wrong.
Any additions to that before Norman asks his second question? Go ahead, Norman. Ask the second question.
Yeah, thank you. So my other question is, I actually went over to like another lab mate maybe like 2 weeks ago, and I asked this question to him because our lab does some work on like solid electrolytes, solid state electrolytes, and they're sort of in the gray zone between like single ion conductors and liquid electrolytes. And going back to like what we would learn in like introductory material science, you have liquids on one end, solids on the other, and then I guess like lithium ion solvation or conduction mechanistically occurs very differently in these two systems. And so Dr. Persson, I think one of the things that you said was when you have highly concentrated electrolytes, the conduction mechanism changes. And my question is about classifying these types of electrolytes as liquids or as solids, or is it somewhere in between? Like is it right to continue to classify them as liquid electrolytes if the conduction mechanism is different? And is there any utility that we could gain by changing the way that we define these systems?
Oh, that's a great question. I'm going to just go on a limb here and state something very categorical. As long as your system is deformable, I would say it's a liquid. Like enough to form, like it can flow into crevices and fill up those spaces, because that's actually one of the real problems with solid state electrolytes, that it's hard to wet your electrode with a ceramic. Whereas those liquid electrolytes, you just sneak in there and you get your transport where it needs to be, even if that transport is hopping through some chain of anions. So Don and Nitash, you can take me up on that.
Well, I will take a little different stance because I think it's very important to go into crevices for an electrolyte. It seems obvious to me. It has to. And another thing that, the reason your hands don't stick when you clap is not because there's not enough van der Waals energy, but because the asperities of your hands are touching each other. If you could somehow get into the crevices of the asperities, your hand would actually stick. And the Post-it stamp, the Post-it guy who actually passed away not a few weeks ago at 3M, figured out how to do this in a solid. In fact, the Post-it composition is, you could call it whatever you want. It sticks because that polymer, which is actually a solid because it doesn't go anywhere, it just stays on the surface. It goes into the crevices of a typical solid. So I think that I feel like liquids and solids are an important classification. There's a bulk aspect to that, and there's a surface aspect to that. And solids have to be better at the interface than they are currently. I think perhaps many of the issues related to solids are because of the inability to go into crevices. Many people think of the materials I work on, which is block copolymers, to be solids. But we find time and time again that they do flow into crevices. Microscopic flow is very different from something sitting on a shelf. I can tell you the block copolymer will sit on the shelf forever, not do anything. But when pressed, it appears to go into crevices as far as we can tell. So I think that, yeah, I think your question is very deep and interesting. I don't know, Kristin, can you say if I was...
No, I think that was great.
Are polymers a liquid then? I'm confused.
You're being confused because you... Anyway. Go ahead, Don. I have taken far too much time.
Well, I really don't have much more to add except, more generally, I suffer from SEI fatigue. And I mean, I've really been sort of hesitant as a scientist to do much with studying the SEI because I think it kind of works in lithium ion systems, and the properties have been optimized over, I don't know, a decade or more. And it seems like, you add a little bit of pixie dust. There's a lot of trial and error and a lot of things we still don't understand. It's too complicated of a system, like I talked about earlier, for me to, well, maybe I'm just not creative enough, but I have not really had a lot of success in framing a good computational problem for the SEI, other than sort of looking at, I don't know, microscopic views of different points of that SEI and different parts of the problem. So, I agree that it's important, but it's not something that I've been particularly excited to study in my career.
I think that Norman's question brings up something that you all work on, and I know because I work in the same program as you, which is this idea of trying to find a theory that then allows you to explain any material. It doesn't matter at least in the bulk, right? Let's start with the bulk and not worry about the interface for now, because that has other problems. And so if you have a theory that explains any state, basically, of electrolyte, whether it's super concentrated liquid or if it's ceramic, and so you think about it that way. From your experience, having spent time thinking about it this way, is it a worthwhile thing for the next generation to consider? I mean, are we wise to try to find ways to build explanations that then we can say, okay, well, the conduction is going to work this way. No matter what material you have, then you just have to worry about mechanics, and then that allows you to choose which way you go, right? Does it make sense now that you've been doing it for a while? What is your take? Is there no hope?
Well, no, I would say, this is a gross oversimplification, but I think that, I think it's true for some computational models. Maybe it's true for many experimental techniques that they're pretty good at telling you, I'm giving good answers for well-posed questions, like maybe a pristine bulk system where there's not a lot of complication. But that's, maybe that's not so exciting. I think it's not so exciting. Pushing the frontiers really requires probing those sticky situations, those complicated scenarios that you find at interfaces, or where the composition is not so simple, or there's trace quantities of something which are doing something interesting and changing behavior. So yeah, I still think there's quite a bit more to be done to look at those scenarios that really strongly influence performance, deviating from, say, simple bulk behavior.
May I say something motivated by Kristin and Don? As academics, I feel we have made our biggest contributions over the years by the real pioneers of the field make important contributions by taking the approach that Don and Kristin have sort of laid out in their, like Don said, I'm hesitant to work on SEI because I can't find a fundamental problem to properly frame it. And Kristin said the same thing in different contexts. I really feel that is, important. I feel like the field of electrochemistry today, oftentimes publications in scholarly journals take on the note that the following scenario. Here is an amazing societal problem, and here's our solution. And look at this amazing battery. It is cycling and we have a few problems to work out. We're not quite sure how this works or how that works or what the conductivity means, but look at the device, it works. I really feel that even for experimentalists, taking what Don and Kristin said, which is, you can start building devices. I don't know what useful thing has come out of all of those papers. And I would say, 50% of the papers I read are at least in that category. But when something is framed properly and then explored in a fundamental way, that knowledge to me is always valuable. So as I do hope that the balance of this shifts towards defining such problems rather than going after complexity.
I love that we're gravitating toward this topic because it's something very similar. Some very similar message came up of the previous panel. And I know that there was some despair in the audience over the fact that, what ultimately gets published are these, groundbreaking devices. So it's good for them to hear from people that are established that, you can still do very well and answer some questions that really move the field forward, more so than a device that, may have more or less complications or more or less realistic prospects. There's one last question that I'm going to read because Saket doesn't have his mic on, and that will take us to the end of the session. It's trying to grab something from what we've discussed and translate it to the electrocatalysis field. So I'm going to read it and see what you think. you can say. What learnings from the battery land or solvation chemistry in general can we apply in the electrocatalysis field to design rational electrolytes? Especially, can we manipulate multivalent cation-based electrolytes in electrocatalytic systems? I'm not sure if you have thought about this before, but if you have, do you have any thoughts? It's an issue of translation. Are we learning things about solvation that then others can use basically in systems that are not batteries to take advantage of what we are learning here?
Okay. Can you clarify? Generally, electrocatalysts are in water. Is that what you're thinking, or what kind?
What we've discussed, yes. So this probably comes from the fact that in the previous panel in electrocatalysis, they were given this idea that because we've discovered that we have to design beyond the catalytic side. And one thing that was underappreciated until recently is just how important the cations in the electrolyte are in the catalytic process. And I think that Saket is going in that direction. Since we are discussing solvation and how to manipulate cations in electrochemical systems, can some of these be used to then manipulate a chemical reaction that's happening at a catalytic surface? It's not very different from thinking about interfacial stability in a battery, right? Where are we with that? Manipulating solvation at the interface to direct chemistry, even if it's interface formation or transformation of a small molecule into something else.
Yeah, I think there's a clear parallel track between what we're doing and they're doing. They might want to promote certain reactivity, like you said, and we're trying to either limit it or influence it in some way. So let's take an example. FEC is an additive that we add to lithium-ion electrolytes to promote higher voltage stability as well as a more stable SCI on silicon. FEC is a minority species when it's bounded to lithium, and it wasn't even clear that it was binding to lithium at all. If it didn't bind to lithium, it would not reduce before EC, and it would not participate in the SCI formation to any larger degree. But it's only by considering that it actually, even in a very, very small amount, still binds to lithium, and then it gets preferentially reduced before EC that we realize how big of an impact it has. So yeah, totally. Solvation will, and tuning solvation with respect to the species and their donor and acceptor number of the different things you have in your electrolyte is going to shift what happens and what happens first, even if it's very, very small amounts. So I think there's tons to learn between our fields, but the problem is always when scientists that are very deep in their fields, when we talk to each other, we have to sort of get through that layer of translation.
So would you say that this is a problem that we're just now starting to, that's the impression that I got from electrocatalysis. Is this the same in the battery space? That's just something that we're starting to recognize and try to investigate?
Well, my experience is that we have not appreciated the impact of even minority species in their solvation on the reactivity of the electrolytes, which is sort of the inverse of what you want from electrocatalysis. So yes, right. We're definitely coming at the same problem from different directions. So we should talk to each other more.
Any other thoughts, Nitash and Don, on that note?
I think that question is a very interesting one. Whenever I listen to electrocatalysis talks, they ignore transport completely. Even sometimes not even mentioning what the concentration of the electrolyte is. Now it might be valid. Water is the most amazing electrolyte you can ever imagine. That's why I was asking you if it's right. Water. Yeah. In spite of that, the idea of desolvation that one of the students, I think his name, brought up, is obviously important. And in water, that solvates so beautifully the cations and sometimes even the anions, for that matter. What happens, how that final desolvation step takes might be the reason why an electrocatalyst works or doesn't work. And I think that is an important recognition, and in that sense, perhaps similar to the kinds of interfacial problems we might be encountering. I would say we still don't know much of that yet. You know, exchange current densities, even in lithium ion batteries, are not agreed upon. Or, you know, maybe an order of magnitude is agreed upon, but not the values. And so there are these questions that are interesting and yeah, worthy of the next generation taking them on.
All right, so we're going to use that thought, and we're 2 minutes over 4:30, and I promised I would keep it to 90 minutes. So especially because that's the third panel. So we're going to leave it there. Don, Nitash, Kristin, thank you very much for your time, for your generosity, and for all the thoughts that you've shared. You've shared thoughts that actually overlap with things that have already come up, which is great because I will say that I did not coach you to say these things. So thank you for your time. Thank you, everybody, for being here. I am going to leave the Zoom open and stay for a few minutes in case anybody wants to hang out and just chat, more as a social component to network. So if you're interested in that, stay on and we can talk a little bit longer. Otherwise, I will see you tomorrow at 10 a.m.